Okay, let's unpack this. Our intuition, when it comes to powerful AI like large language models, often tells us something deceptively simple. The more information you feed them, the smarter they become, the better they perform.
Hmm.
It feels logical, right? More context should always lead to a more informed output. But what if I told you that, for LLMs, that intuitive assumption isn't just flawed, but in many crucial ways, it's actually, well, backwards.
Hmm.
Today, we're diving deep into a fascinating and, frankly, pretty counterintuitive phenomenon called context rot in large language models. It's a core challenge that completely flips our understanding of how these powerful AI tools process information, especially as the inputs get longer and longer. And it has significant implications for how we use them.
That's right. Context rot describes an observed and surprisingly consistent decline in an LLM's performance as the length of its input context increases. Think of it this way. Our human brains expect that if you give us a detailed document, we can reliably access information from any part of it.
Right. Yeah, totally.
We don't assume the details on page 100 are processed differently from those on page 1. But with LLMs, empirical evidence consistently shows that the 10,000th token, the 10,000th bit of information in an input sequence, isn't treated with the same fidelity as the 100th.
Wow.
Performance becomes increasingly unreliable the longer the input gets. It's a fundamental limitation that challenges the very notion of a uniformly accessible context window.
And this isn't some abstract academic problem, right? This is a critical challenge for real-world applications.
Absolutely critical.
Imagine trying to use an LLM to process a massive legal contract spanning hundreds of pages, or conduct an extensive medical review based on years of a patient's history, or even just trying to maintain a coherent, long-running conversation over many turns. If the model starts losing its grip on information buried deeper in the input, its trustworthiness and utility for those demanding high-stakes tasks just plummet.
Exactly. Our mission for you today is to equip you with a comprehensive understanding of this often overlooked limitation. We'll be breaking down the empirical evidence from rigorous research, exploring the surprising characteristics of context rot, and discussing the practical implications and, importantly, actionable solutions emerging from expert studies.
Okay.
By the end of this deep dive, you'll not only understand what context rot is at its core, but also what it truly means for how you interact with and leverage LLMs, especially when you're faced with large amounts of information.
But let's pull back the curtain a bit further then. We've defined context rot as this performance decline with longer inputs. But what makes it such a fundamental problem? Why can't it simply be fixed by just giving LLMs bigger context windows? It seems like it goes deeper than that.
It really does go deeper. Building on that initial definition, context rot is truly the consistent and observed decline in an LLM's ability to perform, even on what should be pretty straightforward tasks, as the input context length expands. It fundamentally challenges the intuitive expectation we have as humans that a system given more information will maintain its processing reliability across that entire dataset.
Right. Like you said, page 5 versus page 195.
Exactly. If I hand you a 200-page report, you expect to be able to recall details from page 5 just as reliably as from page 195. LLMs, as the data unequivocally shows, simply don't deliver on that expectation. And this isn't a superficial bug that can be patched with a quick software update. It's not like that. Instead, it strongly suggests a deep-seated issue within the current architectural designs of LLMs, or perhaps their training methodologies. It implies that the internal mechanisms responsible for processing and, crucially, retaining information over extended sequences are inherently prone to degradation. They just weaken.
So the window isn't really a clear window at all?
It directly challenges that very idea of a context window as a uniformly accessible memory bank for the model. It's more like a foggy window that gets foggier the further you look. And the fact that this decline manifests even on relatively simple tasks under controlled conditions, like we mentioned, just repeating a word.
Just repeating a word.
Yeah, even something that basic. It's a powerful indicator that it's a fundamental architectural limitation rather than just an issue that pops up when the task gets really complex.
And this inherent architectural limitation leads us directly to why context rot isn't just some interesting research topic, but a critical challenge that impacts the real-world deployment and trustworthiness of these models. It's where, the rubber meets the road.
Indeed. While context rot is observable even in controlled, kind of minimal settings, its impact is significantly amplified in the complex, messy scenarios that characterize real-world LLM applications.
All right, the messy stuff.
Exactly. Practical deployments frequently involve processing exceptionally lengthy documents.
Think dense legal contracts, detailed medical records spanning years of patient history, or multi-turn conversational histories that stretch over many, many pages. And these real-world inputs are rarely clean, concise, or perfectly structured, are they?
Definitely not.
They're often filled with irrelevant information, semantic ambiguities, very data structures that models just have to navigate somehow. So the performance degradation we observe in controlled lab environments becomes far more pronounced and problematic when you throw in these real-world complexities, where the signal-to-noise ratio can be extremely low.
So it gets worse out in the wild.
Much worse.
Yeah.
This amplification directly compromises the reliability and scalability of LLMs for critical enterprise solutions. If you're relying on an LLM for tasks like comprehensive document analysis, legal e-discovery, or generating long-form content that needs to synthesize information from a vast source, context rot becomes a major tangible impediment.
I can see that.
Yep.
Let's try to find a specific clause. Consider that exact scenario. An LLM asked to review thousands of pages of corporate documents to identify all instances of a specific clause. If it consistently misses clauses buried deep within a document or misinterprets them because of context rot, the entire system's value just diminishes considerably.
The trust is gone.
Exactly. It's no longer a question of theoretical performance. It becomes a very practical barrier to widespread adoption and dependable performance in the most critical and demanding LLM deployments. The trust that you place in these systems fundamentally erodes if they can't be relied upon to accurately process all the information you give them.
Okay, now that we have a solid grasp of what context rot is and why it's such a critical real-world problem, let's explore its empirical characteristics. How does LLM performance actually fall apart under these long context conditions? This is where the surprising, almost counterintuitive behaviors really come to light. And what's particularly challenging, you mentioned, is just how unpredictable this whole thing can be.
That's a crucial starting point. LLMs consistently exhibit what researchers call non-uniform performance across their context window. This isn't just about a gradual, graceful decline in ability. It means their capacity to process information within a given context isn't consistent. It becomes increasingly unreliable as the input length expands.
So it's not a smooth slope downward.
No, not at all. What's particularly baffling is that this degradation isn't a smooth, predictable, linear fall where you can anticipate exactly when and how the model will fail. Instead, it's often erratic, inconsistent, and somewhat random, even on remarkably simple tasks like, as we said, just repeating a specific word that appeared earlier in the prompt.
Still finding that amazing.
It is. This unpredictable nature makes it incredibly difficult to anticipate exactly when or how the model will stumble, or to effectively debug the issues when they happen. This observation strongly suggests that LLMs lack robust, stable internal mechanisms for consistently maintaining performance across long-range dependencies. It's not simply a performance drop. It's an unpredictable and fundamental breakdown in how they handle extended inputs, making their behavior far less dependable than we'd intuitively expect.
So given that unpredictability, what does this mean for how we frame our questions, especially when dealing with those long documents or, sprawling conversations? If you're trying to find a specific piece of information, does the way you phrase your query make a difference as the context grows, or is it just about getting the information in there somewhere?
Oh, it makes an enormous difference. We observe that performance degrades much faster for what are termed lower similarity needle question pairs as the input length increases.
Needle question pairs. Okay, break that down.
Right. Imagine your needle is the specific piece of information you're trying to extract from a giant haystack of text. Your question is the query you put to the LLM. If your question isn't semantically very similar meaning, it doesn't use very similar wording or isn't closely aligned in meaning to that target information, the model struggles disproportionately, especially when the haystack is very large.
Give me an example.
Okay, say the document says the cat sat on the mat, and you ask where did the feline reside? The semantic gap, even though it's small for us, becomes much harder for the LLM to bridge when that information is buried in, say, 50,000 other tokens of text.
Ah, I see. The distance makes the slight difference harder to cross.
Exactly. And this directly mirrors real-world scenarios where you rarely have an exact keyword-for-keyword question-answer match. Semantic ambiguity is common. It highlights LLM's inherent reliance on strong semantic cues for effective information retrieval within extensive contexts.
And this matters hugely for AG, right? Retrieval augmented generation.
Massively. ROG systems are designed to improve LLM accuracy by retrieving relevant info from external knowledge bases and feeding it into the LLM's context. In RA, the quality of the retrieved information, and how well it matches the user's nuanced query is paramount. If the retrieved needle isn't semantically aligned with the question, the LLM has a significantly harder time finding and utilizing the correct information. That leads to less reliable outputs.
Got it. Okay, and what about all the extra stuff we sometimes put into the prompt, whether it's intentionally added or just unavoidable noise from a complex document? Does that just get ignored, or does it actively interfere with the LM's performance, almost like, I don't know, static on a radio?
Unfortunately, it's much worse than just being ignored. It actively interferes. Like insidious malware might be too strong, but it definitely disrupts things. We've seen clear empirical evidence that the mere presence of distractors, irrelevant pieces of information, even a single one, demonstrably reduces LLM performance. Add more distractors, and the degradation compounds, often at an accelerating rate. This impact intensifies with input length, and it's a consistent finding across state-of-the-art models like GPT-4 and Claude.
And some distractors are worse than others.
Yes, that's another key finding. Certain individual distractors cause a greater decline in performance than others, indicating specific toxic elements that models are particularly vulnerable to.
And we can actually see how they mess things up.
Yes, the really telling part here is that detailed failure analysis, where researchers dig into why a model failed, shows exactly which distractors appear most frequently in hallucinated responses.
Hallucinated, meaning made-up answers.
Exactly. The model fabricates an answer because it misinterpreted or was actively misled by the irrelevant information. For instance, if you're asking an LLM to identify a specific financial figure from a report, and a distractor sentence accidentally mentions a similar-looking but irrelevant number, the model might latch onto that distractor and present it as the answer, even if it's completely out of context.
Wow.
This provides crucial diagnostic insights into how models truly break down. It reveals specific vulnerabilities in their attention mechanisms or internal fact-checking capabilities. They latch onto and misinterpret these misleading cues, leading to the generation of incorrect or entirely fabricated outputs. So yes, irrelevant stuff is far from benign. It's a significant source of error and unreliability.
This raises an important kind of nuanced question. We've talked about how the question's similarity to the target information matters and how distractors interfere. But what about the target information itself? If that needle is too similar to the haystack it's in, or maybe too radically different, how does that affect the LLM's ability to find it? Does it blend in too much or stand out too much?
That's a great distinction to make. And yes, we observe a non-uniform needle-haystack similarity effect.
Yeah.
This means the semantic relationship between the target information, our needle, and the surrounding context, the haystack, significantly influences how well the model performs. It suggests that how well the needle blends into the haystack can profoundly affect the task difficulty.
So it's a balancing act?
It seems to be. There's a delicate balance needed here. If the target information is too semantically similar to the surrounding irrelevant context, it becomes incredibly difficult for the model to distinguish and isolate it. It just blends in too well, like trying to spot a specific blade of grass in a vast field.
Makes sense.
But conversely, if the target information stands out too much, say, a completely unrelated historical fact thrown into a highly technical engineering document, it might also be overlooked.
Really? Why would that be?
Well, the thinking is the model might have a bias towards contextual coherence or might struggle with highly disparate information. It's almost as if the model assumes everything should be somewhat related, and if something is too anomalous, it might dismiss it as noise or an error.
That's tricky.
It points to a nuanced challenge in information retrieval within LLMs, where the optimal distinctiveness of information within a long context is not straightforward. The LLM has to strike that balance between finding the unique element and integrating it somehow with the surrounding text.
Now, this next one completely blew my mind when I first encountered it. It challenges everything you'd intuitively think about organizing information, especially if you're used to, say, writing a clear, concise report or building a well-structured argument. It's genuinely counterintuitive.
It is perhaps one of the most surprising and challenging findings in this whole area of context rot. It really makes you stop and think. Empirical research consistently shows that structural coherence actually harms model performance.
Wait, harms? So being logical is bad?
In this specific context, yes. What this means is that LLMs perform worse when the haystack, the input context, preserves a logical flow of ideas, like a well-written document with clear paragraphs, headings, and a natural narrative progression.
That's why.
And here's the kicker. Consistently shuffling the haystack, making the information less logically organized, or even totally randomizing the sentence order consistently improves performance.
Improves by shuffling it.
Consistently improves. This observation profoundly challenges human cognitive models, where we naturally assume logical flow aids comprehension and makes information easier to process. For us, structure helps.
Right, absolutely.
For LLMs, it suggests a fundamentally different processing paradigm in long contexts. It appears that LLMs may struggle with maintaining a global understanding of a coherent narrative. Or maybe their attention mechanisms become overweighted by local dependencies when information is logically structured.
Meaning they get stuck on nearby sentences.
Sort of. It's almost as if the logical connections between sentences or paragraphs, which help humans build a mental model of the text, somehow confuse the LLM's ability to pull out discrete facts. Shuffling the input might inadvertently force the model to treat each piece of information as a more independent unit, potentially making isolated fact retrieval easier because it's not trying to integrate it into a cohesive, long-range narrative.
So breaking the flow helps it see the individual pieces.
That seems to be the implication. It implies a profound difference in how LLMs process sequential, structured information versus discrete, unordered facts. It potentially points to limitations in their ability to perform complex relational reasoning over long distances, which is a really big deal for how we design inputs and even how we think about LLM comprehension. Are they really understanding or just pattern matching in a very sophisticated way?
That's truly fascinating and so unexpected. So, okay, it's not just about finding the info or how structured that info is, but what if the info is buried in a long conversation? Or what if we need the LLM to write an equally long, faithful response based on that long input? Does context rot extend to those scenarios too, or is it just about input processing?
It absolutely does extend to those scenarios, and it manifests in two significant ways that really underscore its pervasiveness. First, in conversational question-answering tasks. Models demonstrate significantly higher performance when they are provided with what we call focused inputs.
Focused inputs, meaning just the relevant bits.
Exactly. Only the relevant parts of the conversation compared to full inputs that include all the irrelevant conversational context. This substantial performance gap suggests that the very act of adding irrelevant context, which then necessitates an additional retrieval step for the LLM to figure out what's important, significantly impairs the model's ability to maintain reliable performance.
Give me an example of that.
Okay, say you have a 30-turn conversation about a customer service issue, but only turns 10, 15, and 22 are actually relevant to the final question you ask. Including all 30 turns makes the LLM perform worse than if you just give it turns 10, 15, and 22 directly.
So the noise hurts its ability to find the signal, even if the signal is there.
Precisely. This finding is highly relevant for any retrieval augmented generation system. The retrieval component, identifying the truly relevant information from a larger context before feeding it to the LLM, emerges as a major bottleneck. The LLM simply struggles to filter noise in situ. It needs help.
Okay, that's the input side. What about generating long outputs?
Right. Secondly, we see this issue manifest when the required output length scales with the input length, like in text replication tasks, where the LLM is asked to essentially copy or reproduce a long piece of text. Performance consistently degrades across all models in this scenario.
So it can't even copy accurately if it's too long?
It struggles more, yes. This indicates that context rot isn't solely an issue of input processing or comprehension. It affects the model's capacity to generate long, accurate outputs based on those extended inputs as well. For example, if you ask an LLM to summarize a 10,000-word document into a 1,000-word summary, the quality and faithfulness of that summary might decline significantly compared to summarizing a 1,000-word document into a 100-word summary. This points to a pervasive issue affecting both the understanding and the faithful generation capabilities of LLMs when they are under long context pressure. It can lead to critical omissions of facts or even overgeneration of content that wasn't in the original input.
Okay. What's fascinating here is we're not just talking theory or just anecdotal observations. The data actually shows these behaviors in action, right? Researchers have run extensive, meticulous tests, and the visualizations of their results really bring home the profound impact of context rot. Let's walk through some of the key visual insights from their empirical investigations.
Absolutely. Visualizing the data makes it incredibly clear. One of the foundational visualizations comes from tracking the performance of various state-of-the-art models, including Cloud Sonnet 4, GPT 4.1, Qwen 332D, and Gemini 2.5, flash on that remarkably simple, repeated words task as the input token count increases. What you see consistently across all these diverse architectures is a general, noticeable degradation in performance with increasing context length. The graphs slope downwards.
So it's not just one model family.
No, this visual evidence provides undeniable proof that context rot is a pervasive issue. It's not limited to a single model, a particular training methodology, or a specific LLM family. The fact that even basic information retention and faithful reproduction are compromised in a long context, shown by this simple replication task, powerfully suggests a fundamental scaling challenge. It seems related to their underlying memory or attention mechanisms, rather than something more complex like sophisticated reasoning. It's like a core wiring issue, so to speak.
It's like searching for a specific quote in a massive book. If your query isn't precise enough, it gets harder and harder to find that quote the more text you have to sift through. The data shows this, right? The less aligned your question is, the deeper the struggle becomes for the LLM.
Precisely. Graphs illustrating the impact of needle question similarity vividly show that clear performance degradation. It accelerates as input length increases, particularly for those low similarity needle question pairs. Imagine the x-axis representing the length of the input context and the y-axis representing accuracy. You see a sharp downward curve, especially for those less aligned queries.
Steeper for the mismatched ones.
Much steeper. This means if your query is phrased in a way that isn't semantically very close to the actual target information within the long context, the model struggles disproportionately to retrieve it. This visual evidence powerfully reinforces that LLMs struggle significantly when queries are nuanced, paraphrased, or not perfectly aligned with the information they're seeking. It highlights a very practical limitation for real-world applications that require flexible query interpretation rather than exact keyword matching. It kind of pushes the burden onto the user to frame their question perfectly.
And those pesky distractors. We talked about how they interfere, but the data really lays bare how much trouble they cause for LLMs, proving they're not just benign noise.
The visualizations for detractors are particularly compelling and offer direct diagnostic insights. You see clear charts demonstrating a direct and often steep decrease in performance as the number of distractors increases within the context. More distractors, lower accuracy.
And the individual troublemakers.
Yes, it goes deeper. Further, graphs show that certain individual distractors cause a greater performance decline than others, indicating specific weak spots or semantic vulnerabilities in the model's processing. For instance, a distractor that looks like a plausible answer but is subtly incorrect might be far more damaging than one that is obviously unrelated.
And you can trace the errors back to them.
Yes, and perhaps most diagnostically useful, bar charts illustrate which specific distractors appear most frequently in hallucinated responses across different models. This is empirical proof that irrelevant information is not benign. It actively misleads LLMs. The differential susceptibility points to vulnerabilities in attention and reasoning. And by seeing which distractors lead directly to fabricated answers, we gain crucial diagnostic information into precisely where the model's attention or reasoning mechanisms break down, causing it to generate incorrect or made-up outputs. It's like tracing the specific pathways of error.
The blending in factor, or the needle haystack similarity, is also visually compelling. It makes you realize how sensitive these models are to the surrounding text, and how finding the right balance of distinctiveness is key.
Indeed. A dedicated graph compares model performance when the needles, the target information, are semantically similar versus completely unrelated to the haystack content. This visualization visually confirms that the semantic relationship between the target information and its surrounding context profoundly influences retrieval success.
And it's not a simple relationship.
No, it doesn't show a simple linear relationship. Instead, it suggests a complex sensitivity. If the needle is too semantically similar to the haystack, it becomes harder for the model to distinguish it from the background noise. It just blends in. Conversely, if it's too starkly different, semantically isolated in a dense, uniform context, it might also be overlooked. Perhaps because the model's attention might be biased towards information that aligns with the overall contextual theme.
So too similar is bad, too different might also be bad.
It indicates that LLMs might struggle with both extreme cases of semantic blending and stark dissimilarity in long contexts, pointing to a very nuanced sensitivity to the immediate environment of the target information. It's not just about being present, it's about being optimally distinct somehow.
Remember that truly counterintuitive finding about shuffling the haystack, which challenges our very notion of organization. The data makes it absolutely undeniable. It's truly striking to see it visualized, almost forcing you to reconsider how you approach information.
This is, as you said, one of the most significant and surprising findings, and the visual evidence is particularly powerful. It really jumps out at you. The visualization shows average performance across no less than 18 different models. And it strikingly illustrates that models consistently perform better on shuffled haystacks compared to original logically coherent ones.
So you see a graph, and the shuffled results are just higher.
Consistently higher, yes. Imagine a bar chart where the shuffled bar is consistently taller than the original structured bar across a wide range of models and context lengths. This fundamentally challenges the assumption that LLMs process information in a human-like, sequential, and coherent manner over long contexts.
It really does.
Visually, it strongly implies that LLMs struggle with maintaining a global understanding or coherent narrative structure over long inputs. Instead, they might be more adept at identifying isolated facts or patterns in a disordered sequence, possibly due to limitations in their attention mechanisms to effectively integrate information across long, logically connected spans.
So the structure gets in the way of finding facts.
It seems counterintuitive, but the data suggests that might be the case. It suggests a profound difference in LLM comprehension compared to human understanding, where logical flow is paramount for making sense of complex information. It makes you wonder, are they building a mental map of the text like we are? Or are they just pattern matching discrete tokens in a very different, maybe shallower way?
Finally, let's look at how LLMs handle conversational data, which is so common in real-world applications, and just, well, trying to replicate text accurately. That seems like such a basic task for any language model.
The long meaningful results provide clear visual evidence here. Long meaningful is a specific benchmark designed to test an LLM's ability to retain information over long conversational histories and various forms of extended memory. Graphs from this benchmark demonstrate a significant performance gap between providing models with focused inputs, just the relevant parts, versus full inputs that include all the irrelevant context for conversational QA tasks.
And this is across different models.
Yes. This holds true across various model families like Claude, GPT, Gemini, and Qwen. It unequivocally demonstrates that the retrieval or context filtering step is a major bottleneck in conversational settings for LLMs. When models are forced to identify relevant information from a larger, noisy context, their performance drops significantly. This is critical for IG systems, emphasizing the need for highly effective pre-retrieval or in-context filtering mechanisms before the LLM even sees the data.
And does it vary by question type?
Yes, other graphs show how performance varies across different question types within these conversations, whether they require factual recall, temporal reasoning, or knowledge updates across turns. This suggests that context rot isn't uniform across all cognitive demands. Some tasks suffer more than others.
Okay, and the copying task, output fidelity.
Right. Regarding output fidelity, other graphs focusing on the repeated words task show that accuracy is consistently highest when the unique word is placed near the beginning of the sequence. This indicates a strong primacy effect. Information at the start of the context window is retained and processed more reliably than information in the middle or end.
So put the important stuff first.
That's a crucial practical observation for context engineering, yes. What comes first often sticks best. Furthermore, graphs quantifying the difference between input and output word counts in these replication tasks vividly illustrate that context rot doesn't just impact comprehension. It also affects the fidelity of output generation. As context length increases, models are more prone to either under-generating omitting information or over-generating adding superfluous content when they are dealing with long inputs.
So they add stuff or leave stuff out more often.
Exactly. This suggests a broader degradation of the model's internal state and control over its generation process, not just its ability to understand.
So what does all this mean for us? For those building with LLMs or just trying to get the best answers from them in their daily work, these aren't just fascinating research findings. The good news, I hope, is that these insights translate into actionable strategies we can use right now to mitigate the effects of context rot.
That's right. The most immediate and profoundly actionable mitigation strategy for practitioners today revolves around what we call context engineering. This means the careful construction and meticulous management of the model's context window. How you present information matters hugely.
So it's about how we feed the beast.
Precisely. The way you present information to an LLM profoundly influences its performance, making effective context engineering absolutely essential for reliable outcomes. It's about being smarter with your inputs.
Okay, what's strategy number one?
One key practice is to prioritize key information. Given that strong primacy effect we just discussed, where accuracy is highest for information placed near the beginning.
Put the important stuff first.
Exactly. Critical information should always be positioned at the start of your prompt or context window. If you're asking an LLM to answer a question from a document, place the most crucial sections of that document right at the top of your input. This directly leverages the model's observed tendency to retain information more reliably from earlier positions.
Makes sense. What's next? Dealing with the noise.
Yes, you need to minimize and strategically manage distractors. As we've seen, even a single irrelevant piece of information can reduce performance, and more distractors compound this into a significant problem. So actively reduce irrelevant information within your context. This often means pre-processing your data to filter out noise before it even gets to the LLM.
Clean it up first.
Clean it up. If distractors are unavoidable, consider their semantic type. Some are known to be far more detrimental, often leading to hallucinations. For instance, if you're processing a legal brief and there are irrelevant case citations or tangential discussions, try to prune those out. This involves very careful filtering and curation of your input data.
Okay. And then there's that weird finding about structure.
Right. Then there's the truly strategic and often counterintuitive structuring of your input. For tasks that primarily require discrete fact retrieval, where you're asking the model to pull out specific pieces of data like names, dates, numbers, it might actually be beneficial to present information in a less overtly structured or logically flowing manner.
So, shuffle things up. Seriously.
It sounds odd, but remember that finding about shuffling improving performance. This challenges our traditional document design. While it might feel wrong, presenting information in a list of bullet points or even deliberately randomizing sentence order for highly factual, non-narrative content could yield better results than a perfectly written paragraph.
Or use separators.
Alternatively, yes, using explicit delimiters like hashtag tag tag or XML tags to clearly segment information rather than relying solely on narrative coherence can also be explored. It requires a shift in thinking optimized for the LLM, not necessarily for human readability in the input.
Okay. What about RD systems specifically?
For those working with retrieval augmented generation, semantic alignment of retrieved chunks is absolutely crucial. Ensure that the chunks of information you retrieve from your knowledge base are highly semantically aligned with the user's query. If a user asks about the best way to prepare for a marathon, your retrieval system should ideally pull up info specifically about marathon training techniques, not just general running tips.
Better match, better answer.
Exactly. This significantly improves needle question similarity, reducing the burden on the LLM to identify relevant information from semantically distant or ambiguous queries. The better the match, the less the model has to infer, and the more reliably it can perform the task.
And the classic solution. Just make it shorter.
Pretty much. Finally, a common and highly effective strategy is chunking and summarization. Pre-process very long documents into smaller, more focused chunks or concise summaries. This effectively reduces the overall context length that any single LLM call needs to handle. Instead of giving the model a 100-page report, you might give it 10-page summaries, or maybe just the 100 most relevant paragraphs identified by some other process.
Break it down.
Break it down. This alleviates the burden of in-context retrieval and long-range processing, presenting LLMs with more focused and manageable inputs. It directly mitigates context rot by simply not asking the model to process too much too often in one go.
Okay, those are some really practical, immediate fixes. But beyond these workarounds, what about the long game? How do we fundamentally improve LLMs so that context rot becomes less of an issue down the line rather than just something we constantly have to engineer around?
That's where fundamental research comes in, really pushing the boundaries of what these models can achieve. Firstly, there is a critical need for more rigorous long context evaluation. Current benchmarks, like the simple needle in a haystack tests, while useful for initial diagnosis, are often inadequate. They tend to underestimate the real-world complexities of long-context use cases.
So they make the models look better than they are in real situations.
Potentially, yes. They might lead to an overestimation of LLM capabilities. They might tell us if a model can find a specific word, but not if it can reason across a complex, multi-paragraph argument buried in noise. We need to develop new, sophisticated benchmarks that incorporate these real-world complexities. semantic ambiguity, diverse distractor types, nuanced question answering over complex narratives, and challenging reasoning tasks that require integrating information from across vast distances in the context.
Better tests for better models.
Exactly. Without better, more representative evaluation metrics, it's difficult to accurately measure true progress in effectively mitigating context rot and to push the boundaries of what these models can truly do in real-world scenarios.
Okay, what else on the research front?
Secondly, researchers need to focus on disentangling task difficulty from input length. It's crucial to systematically separate how much of a model's performance degradation stems from the inherent difficulty of the task itself, like a task requiring deep logical inference, versus its ability to effectively handle long contexts.
So is it the length itself, or just that longer tasks are often harder?
Right. By isolating the impact of context length from overall task complexity, we can more precisely pinpoint whether LLMs are failing due to a fundamental inability to process long sequences, or if the task simply becomes inherently harder when more information, even relevant information, is available. This distinction is essential for guiding future efforts. Should we focus on architectural improvements to the LLM itself, like designing better attention mechanisms, or focus more on refining prompt optimization and external data preparation techniques? It helps us direct our research efforts more efficiently.
And looking even deeper inside the models.
And finally, yes, a cutting-edge area of research is mechanistic interpretability. This involves a deeper investigation into the underlying mechanisms behind performance degradation. How does structural context actually influence the LLM's attention mechanism? Why are certain types of distractors more harmful? We need to understand the why inside the black box.
Opening up the black box.
Trying to, yes. By analyzing how internal components of the LLM are affected by long, complex, or structured contexts, researchers can identify specific architectural weaknesses that contribute to context rot. This is about moving beyond empirical fixes, like shuffling to principled, architecture-level solutions. The striking observation that shuffle haystack structures improve performance, for example, particularly underscores this need for interpretability. It defies superficial explanation and strongly suggests a complex, non-human-like interplay within the model's processing that we desperately need to better understand to truly build more robust and reliable large language models.
So what does this all mean? We've seen that context rot is this pervasive, really counterintuitive challenge for LLMs. It fundamentally challenges our very ideas about how they understand information. It's not just about token limits, it's about how these models truly process, retain, and synthesize information over extended sequences in ways that are often very different from how our own brains work.
Indeed, it demands a dual approach, really. Immediately, for anyone working with LLMs today, context engineering becomes absolutely critical for current reliability. This means meticulous and sometimes counterintuitive prompt design and data preparation strategies, prioritizing information, minimizing specific detrimental distractors, and strategically structuring input data, even if it feels unnatural.
The practical stuff we can do now.
Exactly. This user-side mitigation is paramount for enhancing the reliability of current LLM deployments in the real world. Concurrently, a concerted long-term research effort is imperative, focusing on more rigorous evaluation benchmarks, disentangling task difficulty from context length, and pursuing mechanistic interpretability to uncover the underlying architectural limitations.
The fundamental research.
Yes, this fundamental research is essential for achieving principal breakthroughs that can fundamentally enhance LLM robustness in long context scenarios, paving the way for truly intelligent, long-range processing in the future.
This deep dive truly reveals a profound difference between how we process information and how LLMs do. It challenges us to rethink our assumptions about AI comprehension. As you go about your day, perhaps consider this. How might your understanding of a complex topic be subtly different if the information was presented to you in a completely disordered way, shuffled like we discussed? Or what if crucial details were buried at the very end, almost out of sight, where your attention might naturally fade? And what does that tell us about the future of human-AI collaboration in navigating complex and ever-growing mountains of information? Something to think about.